In the last class, we talked about SVD decomposition, where we said that we can write any matrix A and decompose it into three matrices U, V, and V transpose, where U is of size M, is an orthogonal matrix of size M cross M. V is of N cross N, and then you have a close to diagonal matrix, which is not a square matrix. It's called M of size M cross N. And the sigma matrix in the center holds the singular values, as we had seen, and the singular values determine how many numbers would be required, and then this compression of this matrix A can be reduced to a certain very few numbers, and that is given by the non-zero singular values. Now, this concept is this is useful also when we talk about something called the least square method, which I'm sure you would have heard about. In these, you have, let's say, a data collection of data for sort of, let's say, you have x1, x2, that's the points x1, x2, and you have a collection of the data, and then these are several experimental data points or whatever observations, and then you want to fit a line through it, right? So what is the solution that you want to get? This is least square method or something that we encounter. What is the optimal solution to this entire setup? So to get to that setup, to look at least square method, what we do is, let's say we have ax equal to b as the system of equation that you want to solve to get the optimal solution. So of course you had a collection of points, but then you want the best possible fit to that solution. So and it's an over-constraint problem. That means you have more equations than the number of variables. What you do is you take a transpose, then the transpose reduces to less number of variables, and you have A transpose AX is equal to A transpose B. That's what you have. Now, if it turns out that A transpose A is invertible, then we can write the solution X as A transpose A inverse operating on A transpose B. And that's something that you call as an optimal solution, the best fit or something. Then we can call this, for this non-square matrix that we had, we can define this way an inverse. Of course, it's not inverse in the actual sense, but it's a inverse defined between sort of the subspaces there, the range and the mapping pack, leaving out the kernel space. So that inverse is in a sense it is an inverse. So we can also see it from SVD in a more straightforward way. Let's say, and if it may turn out that A transpose A is singular in some cases, that then we already know how to deal with it in terms of pseudo inverses that we had learned earlier. So if we have an SVD decomposition for A, like U sigma V transpose, then A transpose A would reduce to something which would be V sigma transpose sigma V transpose, and that you can see you have taken, this is A transpose, this is A. When you take the transpose, this comes here, this becomes sigma transpose, this becomes U transpose, U sigma V transpose. So you have all these quantities, and you know in the center you have U transpose U now, which is an identity thing because U is an orthogonal matrix. So U transpose U is identity, so you can sort of take it off. And what you're left with is V sigma transpose sigma V transpose. Now, inverse of that would be, so if you have to write inverse of that, then you can just use the rule that we had defined earlier for the products. So you will be having V minus T, sigma transpose sigma inverse, and V inverse. Now, because it's an V is also an orthogonal matrix, so V transpose inverse will become V back to V. And this quantity in the center, we'll just keep it sort of carried as sigma transpose sigma inverse. And this V inverse will become V transpose. correct? So now if we have if we define this, start from this definition of A inverse here, we come back here. So if you have A inverse, which is A transpose A inverse A transpose, then you can write the entire thing again. A will use SVD decomposition, which is U sigma V transpose transpose. And when you put them together, you end up getting this quantity. Okay. Now we know that sigma is not a square matrix. So how do you sort of, when you take sigma transpose sigma, there's a possibility that you may actually get zeros, a lot of zeros. So what we do is to define the inverse, and we'll not call it as an inverse in the strict way, because some of the singular values could be zero. If that is the case, then you define something called a pseudo inverse for this specific part, which is diagonal matrix. Then this will be a square matrix in a way. So you will have 1 by sigma 1 square, 1 by sigma 2 square, and the quantities which were zero is just leave them out as zero, because you don't do 1 by 0, you leave them out as 0. So that becomes a pseudo inverse. Now sort of pseudo inverse for that. And now when you use it in this definition and multiply this by sigma transpose will have still the same quantities, sigma 1, sigma 2, sitting in the diagonal entry. Of course, it is a non, but then you will have the diagonal entries would have sigma 1, sigma 2. And then you would multiply these two, you would end up getting 1 by sigma 1, 1 by sigma 2, because it will be one of the powers will be taken away by this multiplication. So then the pseudo inverse A inverse would reduce to something V, which we know already. So if we know SVD, then we know V, 1 by sigma 1, 1 by sigma 2, and then remaining columns you fill with zeros, and then you have U transpose, and this becomes your V sigma inverse in this sense, not actual sense, it's in the pseudo sense. Get this. So this was also called, if I'm right, Moore-Penrose method or pseudo inverse. So Moore-Penrose pseudo inverse. That's how you will define. And once you know this, then you have actually sort of you would have gotten the optimal solution using this, the best fit that you wanted, that you would get from here. So right, so this best solution is like a linear fit, as we've seen. It would set the relation between different components of the vector x. Now coming to the next topic, there are like SVD decomposition, there are several useful decompositions. LU decomposition is very popular. So in this, when we were looking at the definition of inverse by using row operations, we had come across this LU decomposition. So here you can decompose any matrix, square matrix, into lower triangular matrix, and an upper triangular matrix. So called LU, and therefore it's called LU decomposition. For symmetric matrices, you have something called Cholesky decomposition, which is for square, symmetric, and positive definite matrices. And in that case, this same LU decomposition type of decomposition reduces to something called you get lower triangular as U transpose of the upper triangular matrix, where yeah. Now from here, once you get this, you can solve a system easily. You can say that you have, for example, U transpose U x y. If you had this set of equations, and then what you can say is U transpose x prime is y. Now U transpose, if you know, then what you know is that it's lower triangular matrix into x prime. Let's say x prime 1, x prime 2, and so on. And right hand side is y1, y2, and so on. Now from here, the top one has just one element, so this equation is easy to solve. let's call this as A11 or U11 if you can call it. So U transpose 1 1 X, let's call it U transpose X1 prime is essentially Y1. So you can solve it directly. X1 prime is Y1 divided by U11 transpose. Correct. Once you know X1 prime, the next equation you have two terms. One of them involves X11. This term involves X11, and this is corresponding to X1 X prime 2. Now you would have the equations set up like U 2 1 transpose X1 prime plus U22 transpose X2 prime is equal to Y2. Now, because you know this, you take it to the other side and you get solve for X2 prime. This is Y2 minus U21 transpose X1 prime divided by U22 transpose. You can solve for it X2 like this. And similarly, you can continue like this. Once you have solved for all the X1 primes and X2 primes and everything, then what you can do is you can reduce it now your U times X is essentially X prime vector. Now U is essentially an upper triangular matrix. So in that case, you start from it. We also call it, when we do Gauss elimination method, we call it as back substitution sort of thing. So you start with the last one. So UNN xn is essentially xn prime. So you have solved for xn. The next equation is xn minus 1 n minus 1 times xn minus 1 plus there is one that you already know, which is un minus 1 n xn is equal to xn prime, xn minus 1 prime. And when you solve for, from here you can solve for xn minus 1. So it will be like this, divided by u minus 1, and so on. You can go all the way back and then you would have solved it easily. So here you don't have to, if you know the decomposition, then you don't have to actually compute the inverse. Now the last thing, the last decomposition that there are several, so this is, we're going to discuss only these three. I'll mention only these three. We're not going to discuss any of these in detail, any more details. So look at the QR decomposition now. So QR decomposition is interesting. So you say matrix A is written and as can be split into as a product of an orthogonal matrix Q and an upper triangular matrix, which you're saying R as an upper triangular matrix. So you can split always, it always exists. You can always split a matrix A into these this way. Cholesky doesn't exist always. You need a square, symmetric, positive definite mode. This here you just need to deal with. So there is no restriction of that sort in this case. So when you write it, you will have this kind of a setup where you have for Q, which is an orthogonal matrix, would have columns which are orthonormal to each other, and this is going to be an upper triangular matrix. And the proof of this is by construction. You can show that any A can be decomposed into this form. And these final utility in when we talk about finding eigenvalues and eigenvectors of a general matrix, large matrix, then this in numerical linear algebra, you can use QR decomposition to help you with that in an iterative manner. So I think I will not go into any more details of these methods, these decompositions. Now we'll move to tensor algebra. Now, tensor, what is a tensor? Tensors, they are also linear transformations. They are essentially linear transformations which map vectors to some other quantities. So they're mostly about mapping vectors. A second order tensor, for example, would map, it's a linear transformation that will map a vector to a vector. So it's a V to V mapping sort of. You can think of from a vector, it will map a vector V to a vector V. Vector from a vector space V to another vector space. Third order tensor is a linear transformation that will map a vector to a second order tensor. And once you get second order tensor, then you can think of it as mapping from mapping a vector to another vector. So that sequence can go. Like you can have a third order tensor, let's call it T3, operating on a vector u to get a second order tensor, and then you can operate it again on, let's say, v vector, and that would be something like this, and then you'll get some double vector. So a third order tensor operating on u gives you a second order tensor, then you operate it on another vector v, and that will give you a vector w. So that sequence you can follow. So in general, the nth and an nth order tensor would map a vector to an n minus 1th order tensor. Okay. Now let's look at R cube space, and on the following, whatever we will discuss, we'll limit ourselves to R cube vector space only. Although most of these concepts will also be applicable to n-dimensional vector spaces, most of them, maybe if not all. Then let's look at vector u. We can write vector u in terms of bases, and we mostly in this, whatever we'll discuss from now onwards, we'll define our bases as e1, e2, e3, which is orthonormal basis, orthogonal basis, or orthonormal basis. They're all unit vectors, right? So that means we can write ei dot ej as delta ij. So if they are the same vector, then you get unit. If they are different vectors, then you get 0. Anyway, you can be represented in terms of a component corresponding to the first basis vector, the second basis vector, and the third basis vector. So you can put it in the summation form as ui ei, where I runs from 1 to 3. This is a summation form using an index. Now we're using index I. Einstein said that a lot of times you have all these summations coming everywhere, then there's what's the point of writing all these summations, because it will become tedious. So he said that if an index is repeated, it by default would mean summation. So that's the Einstein notation. So whenever you see a repeated index, it means that it's going to run from 1 to 3, and it's going to be u1, e1, u2, e2, u2, u3, e3. So in this case, the repeated index means this summation. So the representation is condensed, and the algebra that you have to do becomes less tedious. Now, delta ij, as we had seen, it's a Kronecker delta. And sometimes it's called a substitution operator. The reason is the following. You have xi delta ij, and it will say xi delta ij, I being repeated, but then because delta ij is non-zero only when j is equal to I, otherwise it will be 0. So this summation will reduce to only one vector, one component xj. So therefore it has transferred the index I from this to the index j in place of I. So delta ij would replace everywhere, wherever I is there, you can replace with j. So this is also, you can also think of it having an index transferring property. For example, delta ik, delta kj will replace everywhere there wherever there is a k, because k is repeated, so it essentially means summation. But then because the summation is sort of this term is Kronecker delta, so it will be non-zero only when k is equal to j. That means you have to just transfer the index, and delta ik, tau ik, delta kj would reduce to just tau ij. So this summation will become sort of reduced to this only one term. Now we can put the elements of delta ij in a matrix form in this way, let's say. So delta 1, 1 is essentially, you can think of it as also ei, e1 dot e1, e1 dot e2, and so on. So because e1, e2, e3 are all orthogonal vectors, so they will all, the dot product will all go to 0 wherever I is not equal to j, and e1 dot e1 is 1, e2 dot e2 is 1, and e3 dot e3 is 1. Now you can see when you repeat the index delta ij, it will become uh, delta j is I. That means you're talking about this. You'll repeat it means it is delta 1 1, the summation, and Einstein notation summation. So delta II means delta 1 1, delta 2 2, delta 3 3. And in this case, they're all 1 1 1. So the net sum is 1. So trace of delta, if we can treat it as a tensor, is essentially 3. And it is a symmetric, of course, by default, because delta ij equal to delta ji is equal to 1 if I is equal to j, is 0 equal to 0 otherwise. So delta ij is same as is equal to delta ji. That property is satisfied. So you can switch the indices and the value won't change. So this helps in many places in when you're um working with doing algebra on complicated expressions. It helps you reduce the expressions to bare minimum. So moving forward, then you have an example for third order tensor would be this permutation tensor, which is epsilon, which is represented as epsilon ijk, and it's called Levi Civita symbol. And this is just, it just means that whenever they are in an order, if you can follow the circle, this is what the circle that we normally use when we denote our I cap, j cap, whenever we want to use cross product, and therefore epsilon appears in a lot of cross products, as we will see. So the quantity epsilon 1, when they are in an order 1 2 3 in this order, then you can define the quantity as 1. So 1 2 3 is 1, 3 1 2 is 1, 2 3 1 is 1. When you change the order, when you reverse the order, you say 1 3 2, then you get minus 1. 3 2 1 again minus 1, and 2 1 3 is also minus 1. So when you move in the anti-clockwise fashion, you get minus 1. When you move in the clockwise fashion, you get 1. So, and you can also think of it as a sort of a circle here. So you can, if you are taking 1, you take it back, it becomes 2 3 1. If you take 2 back, you get 3 1 2. So that's where you can think of doing uh, manipulate all manipulations, and all these three quantities will give you 1. And there are only these 6 possibilities, because this is the permutations that you will have from the arrangement that you will get for these 3 numbers is given by 3p2, and that gives you the number of arrangements 6, and these are the only possible arrangements, 6 arrangements. Half of these arrangements corresponded to value 1, and the other remaining half correspond to minus 1. And if you have a repeated index, 1 1 1, for example, will give you 0, 1 1 2 will also give you 0, 1 2 2 will also go to 0. All the remaining quantities, whenever you have a repeated index, you will get a 0 quantity. So the tensor epsilon ijk can have values 1, minus 1, or 0. Our Kronecker delta tensor, second order tensor, had only 2 values, 1 or 0, as its elements. Now, you can also think of it as if, like, if you put a mirror and then you reflect, uh, you can think of it as a mirror ijk, and this is ijk, and you're placed across the mirror j, you put it here and k there, and don't change the way in which you will go in the counting. So here, this thing will correspond to minus of this. So if you say I cross j is k cap, then you will say I cross k is minus j cap, or j cross I is minus k cap in this place. So and you can, these are simple cross products that we already are aware of. J cross k cap is I cap, and k cross j cap is I minus I cap. So these are the values that you get when you're taking cross products. So now relate these cross products with what we were doing here in this uh, when we discussed Levi Civita symbol. This is essentially similar. So what we do is what these signs plus and minus, they essentially correspond to this, whether you go clockwise or anti-clockwise. So we just take clue from there and we can write any cross product between, let's say, ej and ek vectors would be can be written as epsilon ijk ei. Okay, because your epsilon ijk will ensure that when you go in an order, whether it's plus value, whether it's plus k cap or minus k cap, that it will determine. So now we can sort of get rid of this summation by using Einstein's notation. You can just say this is epsilon ijk and I is repeated. So you know it's a summation over epsilon 1 jk e1 plus epsilon 2 jk e2 plus epsilon 3 jk e3. And this would be true for all I, j, k, and k running from 1 to 3. So our indices will run only up to 3 because we're dealing with 3D spaces. So our vectors will have that length. So a vector v, let's say if we write as vj ej in its component, v1 e1 plus v2 e2 plus v3 e3, and similarly w can be written as wk ek. Now k is repeated, so k runs from 1 to 3, and this is summation. Now, if you take cross product between V and W, you will get Vj Ej cross product with Wk Ek. Now, these are scalars, so they don't really change the final quantity. They just scale the final quantity, final vector quantity. So we'll say just pull them out, and this is in the initial notations. This would be a very convenient way of doing manipulation, that you pull out all the scalars and then deal with the vector quantities separately. So we pull out Vjwk, and what you're left with is Ej cross Ek. Now this is what we have already seen what it turns out to be. It is essentially this summation epsilon ijk ei. So this your V cross W can be written in terms of its components of V and W. The Levi-Civita symbol, which is a permutation symbol, and ei vectors. So this is the summation over this. J is also repeated, K is also repeated, and I also repeated. So then finally it is summation over all the ijk's. Now, if we take, let's say, another vector u, which is we are writing as ulel, and take dot product with v cross w, then v cross w is vj wk epsilon ijk ei. So summation over that. And ULEL is here. Now again, the scalar quantities just scale the final quantities, and we'll deal with the vector separately. So we pull out UL, VJ, WK, and epsilon ijk is also a scalar quantity. It's not a vector, it's a number. Depending upon quantities 1, I, and j, and k, we'll take a value. So we just take out that value also. And what we get is EL dot with EI. That's what we get. Now EL dot EI is essentially, because these are basis vectors of an orthogonal basis, then this will be delta Li. So we get delta Li here. Now we expand. Now what we do is, because we take the value L and replace it with I everywhere, so that we reduce this expression to now L is transferred to I, so this becomes I. So this is UI Vj Wk epsilon ijk. So you get this final scalar. So u dot v cross w, which is also a scalar, has this value, which is this is essentially a summation over I, summation over j, and summation over k. Correct? Repeated index. So now we can denote, we sort of introduce this notation that u comma v comma w in these square brackets is defined as essentially this quantity that we get when you do u dot v cross w. Correct? We get this quantity. So it's just defined like that. It's easy to write instead of writing cross one dot everywhere. You just write denote it by this. Now this quantity from here, whatever we had derived, is essentially ui vj wk epsilon ijk. So it's a scalar quantity given by this. And if you would expand, you would be essentially writing u1 v1 w1 epsilon 1 1 1. You see, so there would be a lot of redundant terms if you expand, which should go to 0 because it's epsilon having a repeated index would give you a 0. So 112 is also repeated, so you get 0. So you have a lot of zeros here. Anyway, so if you want to sort of write slightly differently, you can because you know the property that if you change the indices here in a cyclic manner, they don't really change the value. So in this case, what we're doing is we're sort of changing the notations. I is just changing the notation because it's whether you write I, J or K, which takes values from 1 to 3. So you can choose to give it whatever name. So here what we do is we change the name. We say here, let's call I as J, J as K, K as I. We just choose a different name here. So we say I is J, J is K, and K is I. If we do this name changing, then this expression can be also written as this. Because finally, it doesn't have any of the free indices, which means all the indices are being summed over. There is no quantity which is left, no index which is left without having summation done on it. So summation done means it has already taken values 1, 2, 3, 1, 2, 3 several times over. In this summation, for example, like this. So now what we say is JKI, we know, we can if we move in a circular fashion, that means if we write JKI and replace it with IJK. So IJK, if we do a cyclic change, then the value is not going to change. We just write this as epsilon ijk. Now what we see is rearranging. We'll say we can write this as wi uj vk epsilon ijk, and it turns out this expression is essentially in the vector form. It will be written in this form: w dot u cross v, which tells us that these values that we get uvw, that means u dot v cross w is same as v dot w cross u, and this is same as w dot u cross v. You can think of it again cyclic. So if we push it back, push it here, we get v dot u cross w cross u, and then again we push it back and push this one here, we get w dot u cross v. So all these things have the same value, identical value. But if you make a change which is not cyclic, that means if we just swap these two, which is not a cyclic change, in that case, let's see what we get. You get this entire UWB would be written as UI WJ VK epsilon IJK. That coming from previously whatever we had derived, right? This is essentially writing U dot W cross V, and they're writing as WJ VK epsilon IJK. And then you're dotting with U, which gives you UI. So this is what this quantity is. Now we can again do this change J and K. So we replace because we want to get back to whatever expression that we had for previously for these quantities, this quantity. So what we do is we change it, switch the indices so that we get that change. So we write this as UI VJ WK, and let me write it differently. Let's write this as I, because K and J have been swapped. So KJ, right? So these two expressions are same. Here we have not made any change. Now we use the property of epsilon. So if we make this swap, essentially that will give you a negative of epsilon ijk. That's the property that we had seen earlier. And which means this gives you minus of ui vj wk epsilon ijk. Now we know this quantity is essentially minus of u dot v cross w. So now we can deduce that if you make this kind of a swap non-cyclic change, then you get a negative value of what you were getting earlier for the cyclic changes. Correct. So now let's look at in a more simple fashion what v cross w does. Let's sort of write it as v cross w as v j w k e epsilon I j k e I. Correct. Now in the expanded form, we can write this as E1, which is if we take the summation over j and k and I in a certain way. Let's start with E1. So I is 1. So you have 1 and then summation over j and k. Now there were terms which were having repeated index, so they have all gone to 0. So retaining the non-zero terms only, we get V2W3 epsilon 123 and V3W2 epsilon 132. Now you can see that this change we have made here is non-cyclic. That epsilon 132 has a value of -1. Epsilon 123 has a value of 1. Correct. So similarly, E2, if you change I to, if you take the value I as sort of equal to 2, you will get the second term E2 times. Now again, keeping only the non-zero terms. So W1, V1, W3, epsilon 213. This I is 2, V is J is 1, K is 3. You have these quantities, and here you'll have other possibilities that you have J and K switched, which is V3, W1, but this 3, 1. So this is again a minus quantity. No, this is the minus quantity this time. And this is the plus quantity because this is cyclic. If you put 1 here, it becomes 1, 2, 3. Whereas this will not give you 1, 2, 3. It will give you the other way around. Uh, 2, 1, 3 or 1, 3, 2. So this is negative, this is positive. Similarly, E3 can be written in this form. Okay. So so there were, of course, other terms in the summation which have all gone to 0 because epsilon for repeated values goes to 0. Now we can see that this quantity looks like determinant of V2, V3, W2, W3. So because you have a minus sign here, right? So you get the same thing. You can see that it's like that, and multiplied by E1. So E1 into determinant of this, right? You get, if you do this, you get the first term, correct? So similarly, if you will take minus E2 and then take these for this submatrix here, you will get the second term. And if you put E3 here and this as the submatrix, you'll get this. So essentially, this means that we can write V cross W in this matrix form as E1, E2, E3, V1, V2, V3, and W1, W3 arranged in this fashion. When you take dot product with U, what you do is you essentially replace E1, E2, E3 with the values U1, U2, E3. So the this quantity U dot V cross W becomes determinant of this matrix U1, U2, E3, V1, V2, V3, and W1, W2, W3. Arrange the vectors U, V, W put as rows of the matrix. So that determinant gives you this quantity. Now, if we choose EI, U as EI, V as EJ, and W as EK, some sort of vectors, then EI, EJ, EK, essentially, when you would write EI dot EJ cross EK, you will get the permutation tensor, third order tensor, which will be nothing but determinant of EI. U1 is essentially EI dot E1, U2 is essentially EI dot E2, and U3 is essentially EI dot E3. And same way you have quantities here EJ dot E1, EJ dot E2, EJ dot E3, and so on. Correct? Now that means you can write the third order tensor as determinant of this quantity because even in EI they would be orthogonal, although you have to substitute the value of I. So if you put I as 1, you will get a non-zero term here and these will be 0. If you put I as 2, you'll have a 0 here, but then 1, 1 here. So it depends on the values that I, J, K will take. Correct? So, and that means that according to what values you will want to compute for the third order tensor, which component you want to compute of the third order tensor. Now, ei dot e1 is nothing but delta I1. Ei dot e2 is delta I2. Ei dot e3 is delta I3. And same way you have delta J1, delta J, delta J3, and so on. So essentially, you've written epsilon ijk as determinant of these quantities of Kronecker delta, correct? The components of a Kronecker delta tensor, right? Uh, so if you would take product of, let's say, two of these third order tensors, let's say epsilon ijk multiplied by epsilon pqr. Let's say if we do that, these are two third order tensors. Product of two third order tensors is what we're defining here. And that will be essentially determinant of, this is some product, okay, some definition, some product we're defining, so don't take it like a product of linear transformation, which you are A to B and B to C. This is slightly different. So if you have taken determinants, you have two determinants now multiplying, and because determinant of A into B is same as determinant of A into determinant of B, so using this property, what we can do is we can write using this property, what we can do is we can multiply these two and write them in this fashion. Before we do that, what we do is, just because it will help us in manipulations later, what we do is we take we use the property that determinant of A is same as determinant of A transpose. So we take this transpose and write this as delta P1, delta P2, delta P3, and then we take the product. When we multiply these two, we get delta I1 with delta P1, delta I2 with delta P2, delta I3 with P3, right? And similarly here you will get delta I1 with Q1, I2 with Q2, and so on. Putting together, you can write this summation, because there's a repeated index clearly here. You can write this as delta IM and delta MP, if I can choose to write it this way, because delta P1 will be same as delta 1P. So using this, you can write this summation in short form, short notation as this. And similarly, other notations can be also reduced. For example, this would be delta JM and delta MP, and so on. So you can write all the 9 components this way. So they would look like something like this. Now, because M and again, we know that delta MP will be non-zero only when M is equal to P. So that would sort of, you can transfer the index and write this quantity, this summation, as only delta IP, right? Similarly, you can write this one as only delta IQ and delta IR from here, right? Similarly, other quantities like JP, JQ, JR, KP, KQ, KR, they're all coming, all right? So what you have done is you reduce this epsilon ijk into epsilon pqr into this form. Now, if you take the determinant, it will be delta ip, and then you have delta jq into delta kr minus delta jr into delta kq, and other terms will come from here, minus times delta iq, delta jp, delta kr minus delta jr to delta kp, and delta IR into delta JP delta KQ minus delta JQ delta KP. So this is how you get. So finally, because there is no repeated index here, as you can see, and every expression will have I, J, K, and PQR, so you get the product in this form. These left hand side you have 6 indices, right hand side you have 6 indices, and there is no summation happening, of course. Now, any more? So, but if you choose one of the indices to be repeated as P, let's say P is I, it has the epsilon ijk into epsilon iqr. Now you have a repeated index, so you're doing a summation over these quantities. product of these quantities, you're summing up some of them. So you are essentially, you have written I as P, so this becomes delta II, and delta II, as we had seen, is value 3. So that is there. Now if you see, because P is I, and if I replace P with I, get JI and KI, correct? So now if you can rearrange this, what you will get is essentially when you send this inside delta IQ inside, you will get this as delta JQ. So these together would become delta JQ, and this quantity with this quantity will become delta UK. Okay, which is what we're writing here. And this quantity again will become delta JR into delta KQ, delta KR into delta JQ, which is negative of this. So 3 minus 1 minus 1 will become single quantity delta J. So you get this identity. This is a very useful identity. Should always remember these. So an easy way of remembering is, suppose if the first index is what is getting repeated, then this is how you write JQ delta JQ, KR delta KR, and the remaining cross ones would be JR delta JR, and the cross KQ would Q delta KQ. So this becomes this. That way you can remember this identity. And if you have two repeated index, now you can plug in this expression, you can plug in this Q as J. When you do that, you see that it reduces to 2 times delta KR. So this, if you have two repeated indexes, this expression becomes this. And now if you have all of them repeated, that means you're taking a product of epsilon ijk into epsilon ijk. This quantity becomes 2 times delta kk, and delta kk has a value of 3, so it becomes a constant of value 6. So these identities are very useful. So all these three identities that I have marked and put in red rectangles are very useful. As we'll see later, when we'll do a lot of manipulations, you will see that they come out very handy. And here is one of the places where we're going to use it for this derivation, this algebraic manipulation of vectors. Let's say we want to take a dot product of u cross v and u cross v. So what is that dot product reduced to? So now u cross v, as we had seen, is nothing but uj vk epsilon ijk ei. Now I'm taking the dot product, and because it's already repeated index, so we have to choose a different index now on this side. UM, VN, EL, LMN. So these are the same quantities. The only thing is we don't want to get, you cannot repeat an index more than 2 times. That becomes very confusing. 2 times means summation, and 1 time means it's going to appear on the left hand side also of the relation. That means it will remain a free index in the equation. So now again, as we had discussed earlier, all the scalars, the first thing that you will do is pull out all the scalars together. If they are, especially if they are not under any derivative, you can do that easily. So these are the 6 scalars that we have that we pull out. So you get uj, vk, epsilon ijk, um, vn, epsilon lmn. And what you're left with is dot product between ei and el, which becomes delta il, which will transfer the index. Now wherever you see I, you can replace it with L. That's what we do. We replace L with I. Essentially we do ulta. We just write L as I. We get epsilon I mn, epsilon I jk, epsilon I mn, and this is the quantity. Now we have seen that there is a repeated index, and this quantity can be written as delta jm into delta kn minus of delta jn and km. Correct? This is what you get. And on the scalar multiplication, the the scaling factors are uj, vk, and vn. These are the components that you had. Now these will transfer indices. Wherever you see m, you can replace it with j, or j with m, and k with n, or n with k. And that's what we do. We see j here, we replace it with the m, and you have already have an m, so you have um into um, and this vk is replaced with v, so you have vn. So this is what you get. Now you know that wherever you have v dot v would be essentially vel, let's say, dot with vl, el, and vm, em, which will be vl, vm, and delta mlm. Now this would mean we can write this as vm, and that's something that we're getting here. We're getting vn, and um, which means this is nothing but u dot u, and this is going to be v dot v. The second term, which is associated with the negative sign here, will be transferring j to n. So wherever you see j, we'll replace it with n. So you have uj, um, and k with m. So vk is written as vm now, and this is vn. Now this quantity is essentially, so if you have two vectors u dot v, if you're writing, you will write this as u, let's say l, el, dotting with v, let's say m, em, and you can write this as ul, vm, delta lm. So you'll get um, vm. Same thing. So you see UMVM here and U and VN. So you can write both of them can be written as product of U dot V into U dot V. So finally, what we have shown is that a dot product of a vector a vector which is obtained by the cross product of two vectors can be written in this form. That's one of the identities that you can use. So this quantity is nothing but U cross V dotted U cross V. So magnitude of a vector that you get by cross product depends on the values norm of u, norm of v, and u dot v. Now, if you move to the second order tensors and look at some properties of that. So a second order tensor, as we had said, is it maps a vector to a vector. So let's say this T is your second order tensor, which is mapping u to v. So T times u equal to v, essentially is a linear mapping now. So if we write it in the expanded form, so you can write the vector u in terms of the basis vectors as u1, e1, u2, e2, u3, e3, and t is operating on it. Now u1 is a scalar, so it's like a scaling factor. You just pull it out. U2 is a scaling factor, pull it out. E3 is pulled out. So what you left with is t on e1, t operating on e2, and t operating or mapping e3. That way you get these thing. So if we write now that t of e1 is mapping this vector e1 to some vector in the other sort of mapped space. So you can write this as some factor of e1 if you choose the same basis to write, because it's a v to v mapping. So you can choose the same basis on both sort of for both the range also as domain, range and domain. You can use the same basis. So you have this, you can write t of e1 as some summation of this. So we choose the values for this particular map because e1 is fixed, so this mapping is going to be fixed too. So we can just look at this mapping, t of e1 mapping. Then it will be alpha 1 1 e1, alpha 2 1 e2, and alpha 3 1 e3. Similarly, t of e2 can be written as alpha 1 to e1, alpha 2 to e2, alpha 3 to e3. Now, what we do is same way t3 can also be written. Now, let's say we choose to write these alphas as tij, some components of t, which we'll see how we get. But let's say we choose to write alpha ij as tij, then you can write this summation as t1 1 e, right, and plus t2 1 e2. So we can say that the first index is repeated. So we write this as T11 E1 plus T21 E2 plus this thing. So which means the first, this is what it means. So so in the expanded form, we can write it this way. Now we take this resultant vector that we take dot product with ek, some vector ek. So we get ek dot tej, t on ej. So t on ej can be written as, we have chosen to write it as tij ei. Now tij is a scalar, so we just pull it out. Ek dot ei gives you delta ki, and delta ki transfer the index. So ek dot tej is nothing but the quantity tkj, right? So which we call as components of the second order tensor. These are called the second order components of the second order tensor. We can write using the same thing. Instead of writing k, we can choose the name I. So you can write ei dot t of on ej would be just tij, correct? Now, if you take this mapping that we had started with, t operating on u giving you v, now you can write this as t operating on u can be written as u1 e1 plus u2 e2 plus so on in this form. U is a u1 u2 u3 are scalars. You can pull them out. You get uj t on ej, and using the previous definition, we could write tej as tij ei. So that's something that we had written here. Tej is tij ei. So we use this here in place of this. So you get and tij ei. So finally, you can just club these two scalars together in this form. You get tij ei, which is equal to the vector v. So now the ith component of v can be written as tij uj. So we get the mapping, how the mapping is being done. Once we have defined the components of the tensor, now you can write the mapping. So t of u gets mapped to v, and the vector v is now given by this quantity. So the components of the tensor tij multiplied by j and summed over j. So this is essentially ti1 u1, ti2 u2 plus ti3 u3. And then index I, which is corresponding to the component of v, will run from 1 to 3. So v1 would be t11 u1 plus t12 u2 plus t13 u3. Right? Transpose can be written as transpose of t of ij would be nothing but just switch the indices ji. So that's the transpose that you get. You can just use the definition of transpose, the dot product definition, and we think that will give you this property. So now if you have transpose ij as essentially tji, if it is equal to tij, then you call the second order tensor as symmetric. If it is minus times tij, then you call it antisymmetric or skew-symmetric. And as we had seen, any tensor, any general second order tensor can be split into symmetric and antisymmetric as a combination of these two, a linear sort of a sum of symmetric tensor plus an antisymmetric tensor. That's how you can decompose any tensor, second order tensor. Now we can write tensor product of two quantities, which we call as dyadic product. Now the dyadic product is written as A tensor B. Sometimes it's called A tensor B, and it's defined such that if it operates on any vector C, you get B dot C, B dot C, and you get the A vector. Right? So as you can see, any such dyadic product will map any vector. Let's say in this case we have chosen C to a vector A. So you could have chosen any vector that will get mapped to A, which means that the range of this, if we can take this as a tensor, then the range of A tensor B is essentially spanned by only A vector, correct? Now the rank, which means the dimension of range of A, would be then 1. Now, any general second order tensor, we can think of it as each of these is one of the basis part components of rank 1, and a linear combination of these would give you, of that these direct products will give you that any tensor, the tensor T. So in terms of dyadic summation or dyadic products, you can write a tensor T as Tij Ei tensor Ej. And of course, this has to satisfy the property that we had written earlier. That means Ek, this property, that Ei dot T of Ej on Ej should be Tij. So this property it should satisfy, and that you can see is being satisfied. So if I can come here, I take T and operate it on J. So here you'll get this as Tij operating on Ei tensor Ej, correct? So, or I could have, yeah, you get this. So you get essentially Tij Ei, correct? Now you can take a dot product with Ei, and from there you'll get Ei dot T on Ej is essentially Tij. So you get the same components, right? So it satisfies that earlier definition. So you can write your tensor T as a summation of a lot of these dyadic products. So if I can expand, it would be here would be T would be essentially T11 E1 tensor E1 plus T12 E1 tensor E2 plus so on. We'll have such 9 terms. So T would be a summation of these 9 terms. Now, if you take identity matrix, so all the terms which are off diagonal, which means T12 is 0. So if you put T12 0, T11 is 1, and so on. So you'll reduce those 9 terms to only 3 terms, which is E1 tensor E1, E2 tensor E2, and E3 tensor E3. All 3 of them are rank 1, and in such a way they're decomposing that together they're giving you a rank 3 identity tensor, correct? So E1 dot E1, if I have to write as a tensor form, I'll write it in this matrix, which has all zeros except for the first term. This one would be only second term is non-zero, everything else is 0. And in this case, you have only one component, which is 1, and the rest of them are 0. When you sum them up, you get your identity tensor. Now, T of U, if you write, you will write this as Tij Ei tensor Ej operating on U. Okay. Now you can write this as Ej dot with U Ei as the resultant vector. So U dot Ej is Uj, and you get this quantity which is same as Tij Ej dot Uj Ei. So you are reducing it to Tij Uj Ei, which is now Vi Ai. So now what Vi is. Vi is Tij Uj. So here we can also write general dyadic product, general vectors A and B that we have chosen. When we are defining it, we can write A as Ai Ei and B as Bj Ej. And again, as I think we have discussed, all the scaling quantities A and B can be put together outside, and what your remaining the vector operation is done on. So you get Ei tensor Ej. So if you put T as that A tensor P as a second order tensor, then you can write Tij as Ai Bj. Now this is going to be a second order tensor which has rank 1, okay, which would have terms like A1 B1, A2 B2, A1 B1, and then you would have A2 B1, A3 B1, and then here you would have B1 and 2, right? A2, and then A3 B1, and here it will be A2 B3, correct? And This would be A1, B2, A1, B3. And here you would have A3, B2, and A3, B3. So that's how this tensor would look like. This, and this is a rank 1 matrix that you have. The trace of this is essentially TII is AIBI, which is nothing but A dot B. A1 B1 plus A2 B2, A3 B3 is AIBI, which is A dot B. Now let's look at anti-symmetric tensor. These are skew symmetric tensors, or they're also known as that. So to define such a tensor, you can say if we have of course, we have a definition that W transpose should be equal to minus of W. That's what the basic definition of an anti-symmetric tensor is going to be, correct? Now the theorem is that you can write any general anti-symmetric tensor W can be written as, if it operates on U, you can write this operation or mapping as a cross product with a given vector W, which depends on this. The definition of this W depends on the tensor, anti-symmetric tensor W. That's the theorem. And to see, we can sort of by construction, we can see what it will be. So we take W cross U. So W cross U can be written as Wj Uk Ei epsilon I Jk Ei. That's what we had learned earlier. And now we can put Wj and epsilon I Jk together. So we're just rewriting it in this form, the same quantity. Now what we're saying is, because we want to pull out Uk separately, that's why we are doing this. So if you look at Wu now we see that you can write this as the left hand side as Wik, Uk, and Ei. So from here you can say that your Wik would be given by this. So Wik is Wj epsilon Jki. Correct. So why did we write Jki? Because it just we can use the cyclic rule and send the I back. You will get Jki at the end like this. You can also write this as Ijk. So we get this. Now what we say is that if for k equal to I, if you can see from here, if k is I, that means k is I, and epsilon would have a repeated index then. So repeated index would mean that this quantity will go to 0. So you can say from here that Wik, if j is equal to I, will reduce to, if k is equal to I, will reduce to 0. That means the diagonal entries of the tensor, because you're taking k as I, so diagonal entries would be 0. So W11 equal to W22 equal to W33 will all be 0. For an anti-symmetric, for any general anti-symmetric tensor, you can conclude that the diagonal entries would be always 0. Clearly, and then you can see it from here also. You take transpose, if you take W transpose, you will reduce it to, using this scaling, you will reduce it to 0, correct? Using this relation, you will reduce it to 0. Now, if we say W12 is Wj, if we just put values here, so it would be Wj epsilon j to 1. Now, if you have j as any other quantity other than 3, you will get a 0 because you'll have a repeated index here in this quantity. So only quantity which will make it give you a non-zero quantity is 3, and then you will have W3 epsilon 3 to 1, and that will be essentially same as, so here you will have epsilon 3 to 1, which is ulta, which is going to be an anti-clockwise run. So it will have a value of -1. So Wj epsilon j to 1 will reduce to only one component of the vector W, which is W3, and minus times that. And this quantity, because an anti-symmetric tensor, would also be equal to minus times W21. Similarly, W13 can be written as WJ A31, and you will get this W13 component as W2, and W23 component will reduce to minus W1, using the same property. And if you put it back in the tensor, you will see that the diagonal entries are all 0, and the off diagonal quantity is 1, 2, and 1, 3, and 2, 3, and 3, 2. They're all components of the vector W, and this vector W is called the axial vector. Okay, W is called the axial vector. Now we can also do this derivation the other way around. We can say, let's say Wij is given by W omega k or small w k epsilon kji, and now we switch the indices here, and this same quantity can be written as minus times epsilon I j k w k. So the components of W, if you want to see from here, would be the goal is to get the WK components in terms of W. Previously, what we had done was in terms of the axial vectors components, we had obtained W. So we are doing the other way around now, so that you can show that it's going to be unique in a way. So what you do is you multiply both sides by Wijl, and then you can use the property of epsilon ijk into epsilon ik ijl as this is 2 times delta kl, as we had seen. So this minus you send here, and what you get is essentially this index would get transferred, so you get wl, and the right hand side is minus epsilon ijl wij, and this 2 comes here. So you have obtained all the components of, so given an antisymmetric metric tensor, you can always find W. Given a vector W, can always find an antisymmetric tensor corresponding to it. So this is what we have shown. The other property that you get from here is that U dot WU, because of the definition of the transpose, you can write this as W transpose U dot U. Now W transpose is minus times WU, so it will be minus U dot WU. And from there you get that U dot WU is always 0 for every vector U. So for an antisymmetric tensor, U dot WU will always be 0. That means U will be orthogonal to WU. Now for a real eigenvalue, suppose let's say if W has real eigenvalues, then we see that that using this property, that if using this property we can say, let's say if we have W operating on X, then lambda X is what the X is an eigenvector corresponding to a real eigenvalue lambda. Let's say lambda is real. Now we take dot product with X transpose, so X trans with X. So then X dot Wx would be lambda X dot X, which is equal to 0. Which means, but X is not 0 because it's an eigenvector. So that means lambda must be 0, right? So the only real eigenvalues, all the real eigenvalues corresponding to an antisymmetric tensor will go to 0, and it will have only non-zero eigenvalues would be complex. So that's what we get. Another interesting thing that we get is, I think last time we were talking about positive definiteness. So now you know that any tensor A, any matrix A or any second order tensor A can be sort of split it into 2 pieces, one symmetric tensor and an antisymmetric tensor. Let me write this as T. So any tensor T second order tensor can be split into 2 symmetric and antisymmetric components. Now for symmetric tensors, so now if you do S plus A operating on U, and then you take U dot, right? Now this quantity, as you can see, would reduce to U dot SU, because U dot AU will go to 0 because A is an antisymmetric tensor. And then finally, your definition of positive definiteness would sort of reduce to that of symmetric matrices only. So the proof for all the lambdas to be positive that we had done in the last class would suffice. So the last class when we had proven this, that means we were writing lambda 1 u1 square plus lambda 2 u2 square. This will reduce to that, and so on is greater than or equal to 0, means that lambda 1, lambda 2, this is for every u, then lambda 1, lambda 2, lambda 3 should all be greater than or equal to 0 for positive semi-definiteness in the matrix. This is an important point from this that we have gotten. Now let's talk briefly about higher order tensors. Then or maybe we can cover it in the next class. We'll stop here.